The universe is hiding something from us. Every time we try to push the boundaries of speed, reality itself pushes back with forces so violent and absolute that they defy imagination. There's a cosmic speed limit, 300,000 kilometers per second, and the closer you get to it, the stranger and more hostile the universe becomes. Today, we're uncovering why this number holds such terrifying power over the fabric of existence itself. And one quick question: if you could break just one law of physics for a day, which one would you choose, and what would you do with that power? Let me know in the comments down below. I will pin the most creative answer. Now let's begin. The story of light speed begins with a simple question that haunted physicists for centuries. What exactly is light, and why does it move at the speed it does? For most of human history, we assumed light traveled instantaneously. After all, when you flip a switch, the room illuminates immediately. It wasn't until 1676 that Danish astronomer Ole Rømer made the first measurement of light's speed by observing the moons of Jupiter, discovering that light has a finite velocity. But the real breakthrough came in 1864, when James Clerk Maxwell unified electricity and magnetism into a single theory. His equations revealed something extraordinary. Light is an electromagnetic wave, and its speed emerges naturally from the fundamental properties of space itself. The speed of light isn't arbitrary, it's woven into the very fabric of reality, determined by how electric and magnetic fields interact in the vacuum of space. Maxwell's equations showed that the speed of light in a vacuum is exactly 1 divided by the square root of 2 fundamental constants, the electric permittivity and magnetic permeability of free space. This means light speed isn't just a property of light, it's a property of space-time itself. It's the speed at which causality propagates through the universe, the maximum rate at which cause and effect can be connected across space and time. Einstein's special theory of relativity, published in 1905, elevated this cosmic speed limit to a fundamental principle of nature. He realized that the speed of light isn't just the speed of electromagnetic radiation, it's the speed of information itself. Nothing can travel faster than light because nothing can violate causality. If information could travel faster than light, effects could precede their causes, creating paradoxes that would tear apart the logical structure of the universe. The mathematics of special relativity reveals why approaching light speed becomes increasingly impossible as you add more energy. As objects accelerate, their relativistic mass increases according to the Lorentz factor, which approaches infinity as velocity approaches light speed. This means that accelerating a massive object to light speed would require infinite energy, more energy than exists in the entire observable universe. Let's put this in perspective with some real numbers. At 50% of light speed, an object's relativistic mass increases by about 15%. At 90% of light speed, the mass more than doubles. At 99% of light speed, the mass becomes 7 times greater than the rest mass. And at 99.9% of light speed, the mass increases by a factor of 22. The energy requirements grow exponentially, making each additional increment of speed exponentially more expensive. The Large Hadron Collider at CERN demonstrates these principles on a smaller scale. This massive particle accelerator can accelerate protons to 99.9999% of light speed, but even these tiny particles require enormous amounts of energy. The LHC uses superconducting magnets cooled to near absolute zero and electric fields with voltages in the millions to achieve these speeds. The energy contained in the LHC's particle beams, while tiny by everyday standards, is enormous relative to the mass of the particles themselves. Consider what would happen if we tried to accelerate something as massive as a spacecraft to light speed. A typical spacecraft might weigh 100,000 kilograms. Using Einstein's mass-energy equivalence, E equals mc squared, accelerating this spacecraft to light speed would require converting its entire rest mass into pure energy, roughly 9 times 10 to the 21st joules. That's more energy than the entire world produces in several years, and that's just to reach light speed, not accounting for the exponentially increasing energy requirements as you approach that limit. The fuel requirements alone make light speed travel impossible with any conceivable propulsion system. Even if you had a perfect matter-antimatter engine that converts 100% of fuel mass into energy with perfect efficiency, you'd need exponentially more fuel for each increment of speed. The rocket equation shows that the fuel requirements grow exponentially with velocity, and for relativistic speeds, the fuel mass would need to exceed the mass of entire planets or stars. But the challenges go far beyond energy requirements. As you approach light speed, time itself begins to behave in ways that defy common sense. Time dilation means that time passes more slowly for objects moving at high speeds relative to stationary observers. At 90% of light speed, time would pass about 2.3 times slower for you than for people on Earth. At 99% of light speed, time would crawl by 7 times slower from an outside perspective. If you're finding these cosmic speed limits as fascinating as I am, I'd really appreciate it if you could hit that subscribe button and give this video a thumbs up. We're just getting started on this journey through the fundamental barriers that keep us earthbound, and your support helps me continue bringing these amazing discoveries to light. This time dilation effect isn't just theoretical, it's been measured countless times in particle accelerators and is essential for the operation of GPS satellites. The atomic clocks on GPS satellites run slightly faster than identical clocks on Earth's surface because they're moving at high speeds and experiencing weaker gravity. Without corrections for these relativistic effects, GPS would accumulate errors of several miles per day. At light speed, time dilation becomes infinite. From the perspective of outside observers, time would stop completely for anything traveling at light speed. But from the perspective of the light speed traveler, something even stranger happens. The journey becomes instantaneous. A photon traveling from the most distant galaxy to your eye experiences no passage of time during its billion-year journey. From the photon's perspective, it's emitted and absorbed in the same instant. Length contraction presents another barrier to light speed travel. As objects approach light speed, they contract in the direction of motion. At 90% of light speed, an object would shrink to about 43% of its rest length. At 99% of light speed, it would contract to just 14% of its original length. At light speed, the length contraction becomes infinite. The object would have zero length in the direction of travel. This isn't just a visual effect or measurement artifact, it's a real physical transformation of space-time itself. The spacecraft, its occupants, and everything inside would be compressed to zero thickness in the direction of travel. The very concept of a three-dimensional object traveling at light speed becomes meaningless because the object would have no extension in one spatial dimension. The electromagnetic effects of near-light speed travel would be equally devastating. As you approach light speed, the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, would be blue-shifted into high-energy gamma rays. This normally benign radiation, with a temperature of just 2.7 Kelvin, would become a lethal wall of radiation hot enough to vaporize any known material. Even individual atoms of interstellar hydrogen would become deadly projectiles. Space isn't truly empty. It contains roughly 1 atom per cubic centimeter of hydrogen gas. At light speed, these atoms would strike your spacecraft with the energy of high-speed bullets. The thin interstellar medium would become a continuous barrage of high-energy particles that would destroy any spacecraft and kill any occupants. The radiation environment at near-light speeds would transform the universe into a cosmic death trap. The Doppler effect would shift all electromagnetic radiation in your direction of travel to higher frequencies and energies. Radio waves would become microwaves, microwaves would become infrared, infrared would become visible light, and visible light would become deadly X-rays and gamma rays. The universe ahead of you would glow with lethal radiation, while the universe behind you would fade into darkness as all radiation is redshifted beyond detection. This radiation transformation isn't just dangerous, it's absolutely lethal. The intensity of the blue shifted radiation would increase dramatically as you approach light speed. What starts as harmless starlight would become a focused beam of high-energy radiation capable of destroying molecular bonds and ionizing atoms. Any biological tissue exposed to this radiation would be instantly sterilized and destroyed at the cellular level. The cosmic ray environment would become even more hostile. Cosmic rays are high-energy particles that constantly bombard Earth from space, but our atmosphere and magnetic field protect us from most of them. At near-light speeds, these cosmic rays would appear even more energetic due to relativistic effects. Particles that are already traveling at significant fractions of light speed would appear to have enormous energies from your reference frame. The interaction between your spacecraft and the interstellar medium would create a bow shock similar to a sonic boom, but far more violent. As you plow through space at near light speed, you'd compress the thin interstellar gas ahead of you, creating a shock wave that would heat the gas to millions of degrees. This superheated plasma would emit intense radiation and create a brilliant wake visible across interstellar distances. The magnetic fields threading through interstellar space would create additional hazards. As your spacecraft moves through these fields at relativistic speeds, it would generate enormous electric fields through electromagnetic induction. These fields would be strong enough to strip electrons from atoms and create powerful electric currents that could destroy electronic equipment and pose lethal hazards to any occupants. The structural integrity of any spacecraft would be compromised by the extreme forces involved in near light-speed travel. The acceleration required to reach such speeds would create g-forces that would crush any known material. Even if you could somehow accelerate gradually over long periods, the spacecraft would need to withstand the continuous bombardment of high-energy particles and radiation that would gradually weaken and destroy any structural materials. The navigation challenges at near-light speeds would be insurmountable with any conceivable technology. At these velocities, you'd be covering vast distances in very short times, making course corrections nearly impossible. A tiny navigation error could send you millions of kilometers off course, and there would be no time to detect and correct such errors before missing your destination entirely. The communication problems would be equally severe. Radio signals traveling at light speed would barely be able to keep up with your spacecraft. Any communication with your destination would be impossible because your signals would arrive only slightly before you do. Communication with your origin would face enormous Doppler shifts that would make signals nearly undetectable. But here's where the story gets even more interesting. While nothing with mass can reach light speed, there are phenomena in the universe that appear to exceed this cosmic speed limit in fascinating ways. If you're curious about how quantum entanglement, cosmic expansion, and other exotic physics seem to break the light barrier, you should check out my video, "This is why the speed of light is not the fastest thing in the universe." It explores the mind-bending ways that information and space itself can seemingly violate Einstein's ultimate speed limit. The quantum mechanical effects at near-light speeds would introduce additional complications that we're only beginning to understand. At these extreme velocities, the boundary between classical and quantum physics becomes blurred. The uncertainty principle suggests that particles don't have well-defined positions and velocities simultaneously, and at relativistic speeds, these quantum effects become amplified in ways that could affect the behavior of matter and energy. Virtual particles, those quantum fluctuations that constantly pop in and out of existence in the vacuum of space, would interact with your spacecraft in unprecedented ways. The intense electromagnetic fields generated by near-light-speed motion could potentially create or destroy virtual particles, leading to effects that we can't predict with current physics. These quantum vacuum effects could create additional drag forces or radiation that would further complicate high-speed travel. The thermodynamic challenges of near-light-speed travel would be equally daunting. The enormous energies involved would generate waste heat that would need to be radiated away somehow. But at near-light speeds, the normal mechanisms of heat transfer would be severely disrupted. Thermal radiation traveling at light speed couldn't escape from a spacecraft also moving at light speed, creating a thermal trap that would cause the spacecraft to overheat and melt. The life support challenges for any hypothetical crew would be impossible to overcome. The time dilation effects would mean that biological processes would be severely disrupted. The chemical reactions that sustain life operate on specific timescales, and the extreme time dilation at near-light speeds could interfere with metabolism, neural function, and cellular repair mechanisms in ways that would be fatal to any living organism. The psychological effects on crew members would be equally devastating. The knowledge that you're traveling at speeds that compress space and time, surrounded by lethal radiation and moving through an environment that could instantly destroy you, would create psychological stresses that no human could endure. The isolation from the rest of the universe, combined with the knowledge that time is passing differently for you than for everyone else, would likely lead to complete psychological breakdown. The engineering challenges of building a spacecraft capable of even approaching light speed are so enormous that they border on the impossible. Every component would need to be designed to withstand forces and conditions that don't exist anywhere else in the universe. The materials science required to build such a craft would need to advance far beyond anything currently possible, requiring materials with properties that may not be physically achievable. The power generation requirements would dwarf anything we can currently imagine. Even the most efficient fusion reactors would be inadequate for the energy demands of near-light speed travel. You'd need power sources that approach the energy output of stars contained within a spacecraft small enough to accelerate to relativistic speeds. The engineering challenges of containing and controlling such enormous energies would be staggering. The fuel storage problems would be equally insurmountable. Even with perfect matter-antimatter annihilation providing maximum energy density, the fuel requirements for relativistic travel would exceed the mass of the spacecraft by enormous factors. You'd need fuel tanks larger than planets to store enough energy for the journey, making the entire concept self-defeating. The safety systems required for near-light speed travel would need to account for failure modes that don't exist at lower speeds. A minor malfunction that might be inconvenient at normal speeds could be instantly fatal at relativistic velocities. The redundancy and backup systems required would add enormous mass and complexity to an already impossible engineering challenge. The environmental impact of near-light speed travel would be catastrophic on a cosmic scale. The energy expenditure required would be so enormous that it could affect the energy balance of entire star systems. The radiation and particle emissions from relativistic spacecraft could pose hazards to any life forms in their path, making such travel not just impossible, but potentially destructive to other civilizations. The economic costs of developing near-light speed travel technology would exceed the gross domestic product of entire planets. The research and development required would consume resources that could otherwise be used to solve pressing problems like poverty, disease, and environmental destruction. The opportunity cost of pursuing impossible technologies could actually harm human welfare and progress. The timescales involved in developing such technology would span multiple human generations. Even if the physics problems could be solved, the engineering development would take centuries or millennia. The social and political stability required to maintain such long-term projects would be unprecedented in human history. The international cooperation required for near-light-speed travel projects would face enormous challenges. The resources and expertise needed would require collaboration between nations and organizations on a scale never before attempted. The potential for conflicts over technology sharing, resource allocation, and mission priorities could derail such projects before they even begin. The international cooperation challenges become even more complex when you consider the military implications of near-light-speed technology. Any propulsion system capable of accelerating objects to significant fractions of light speed would essentially be a weapon of mass destruction. A small projectile traveling at even 10% of light speed would carry more kinetic energy than the largest nuclear weapons ever built. The dual-use nature of such technology would make international cooperation nearly impossible due to security concerns. The verification and monitoring challenges for near-light-speed technology development would be unprecedented. Unlike nuclear weapons, which require specific materials and facilities that can be monitored, relativistic propulsion research could potentially be conducted in secret, using technologies that have legitimate civilian applications. The inability to effectively monitor such research could lead to arms races and international instability. The space debris problems created by near-light-speed travel would pose existential threats to all space-based activities. Any object traveling at relativistic speeds that collided with space debris would create explosions equivalent to nuclear weapons. Even microscopic particles would become deadly projectiles capable of destroying spacecraft and satellites. The space environment around Earth would become a minefield of relativistic debris. The gravitational effects of near-light-speed travel would create additional complications that violate our understanding of space-time. As objects approach light speed, their gravitational fields would be dramatically altered by relativistic effects. The spacecraft would begin to behave like a miniature black hole, warping space-time around it in ways that could affect the trajectories of other objects and potentially create gravitational waves. These gravitational distortions would affect the spacecraft's own trajectory in unpredictable ways. The interaction between the spacecraft's warped space-time and the gravitational fields of stars and planets could create complex orbital mechanics that would be nearly impossible to calculate or predict. Navigation would become a problem in general relativity rather than simple Newtonian mechanics. The tidal forces generated by a near-light-speed spacecraft would be enormous. Just as the Moon creates tides on Earth through gravitational gradients, a relativistic spacecraft would create tidal forces that could disrupt the internal structure of the craft itself. Different parts of the spacecraft would experience slightly different gravitational accelerations, creating stresses that could tear the craft apart. The frame-dragging effects predicted by general relativity would become significant at near-light speeds. The spacecraft's motion through space-time would literally drag space and time along with it, creating rotational effects in the local space-time geometry. These effects could influence the behavior of gyroscopes, clocks, and other precision instruments in ways that would make navigation and timekeeping extremely difficult. The event horizon effects would create regions around the spacecraft where normal physics breaks down. At sufficiently high speeds, the spacecraft would be surrounded by regions where light cones tip over so dramatically that cause and effect relationships become ambiguous. These regions would be inaccessible to outside observers and could create paradoxes in the flow of information and causality. The Hawking radiation effects that occur near black holes might also manifest around near-light-speed spacecraft. The extreme curvature of spacetime could potentially create conditions where virtual particle pairs are separated, leading to the emission of real particles and radiation. This process could drain energy from the spacecraft and create additional hazards for any occupants. The quantum field theory complications at near-light speeds would introduce effects that we don't fully understand. The interaction between quantum fields and curved spacetime becomes extremely complex at relativistic speeds. The spacecraft would be moving through quantum fields at velocities approaching the speed at which field excitations propagate, potentially creating novel quantum effects that could affect the stability of matter itself. The vacuum polarization effects would become significant as the spacecraft's electromagnetic fields interact with the quantum vacuum. At near-light speeds, the electric and magnetic fields generated by the spacecraft's motion could become strong enough to create electron-positron pairs from the vacuum, leading to a cascade of particle creation and annihilation that could drain energy and create dangerous radiation. The Casimir effect, which creates attractive forces between closely spaced conducting surfaces due to quantum vacuum fluctuations, could be dramatically altered at near-light speeds. The motion of the spacecraft through the quantum vacuum could modify these forces in ways that affect the structural integrity of the craft or create unexpected accelerations that interfere with navigation. The Unruh effect predicts that accelerated observers will detect thermal radiation in what inertial observers see as empty vacuum. For spacecraft undergoing the enormous accelerations required to reach near-light speeds, this effect could create the perception of being surrounded by hot thermal radiation, even in the vacuum of space. This radiation could interfere with instruments and pose additional hazards to crew members. The information paradox problems that plague black hole physics would also affect near-light speed travel. As the spacecraft approaches light speed and begins to exhibit black hole-like properties, questions arise about what happens to information that falls into the spacecraft's gravitational field. The resolution of these paradoxes might require new physics that we don't currently understand. The holographic principle, which suggests that all information in a volume of space can be encoded on its boundary, might impose fundamental limits on near-light speed travel. If the spacecraft's information content becomes encoded on its surface as it approaches light speed, this could affect the internal structure and function of the craft in ways that make travel impossible. The string theory implications of near-light speed travel would introduce additional complications from extra dimensions and exotic physics. If string theory is correct, the extreme energies and space-time curvatures involved in relativistic travel could reveal effects from higher dimensions or create exotic particles and forces that don't exist under normal conditions. The loop quantum gravity effects might impose discrete limits on space-time that become apparent at near-light speeds. If space and time have granular structure at the Planck scale, the extreme conditions of relativistic travel might reveal this discreteness in ways that affect the motion and stability of spacecraft. The causal set theory implications suggest that space-time might be fundamentally discrete rather than continuous. At near-light speeds, the spacecraft might encounter the fundamental granularity of space-time, leading to effects that could disrupt normal physics and make smooth motion impossible. The emergent gravity theories propose that gravity itself might be an emergent phenomenon arising from more fundamental physics. At the extreme conditions of near-light speed travel, these underlying mechanisms might become apparent, potentially revealing that our understanding of gravity and space-time is incomplete. The dark energy interactions could become significant at near-light speeds. The mysterious force that drives cosmic acceleration might interact with relativistic spacecraft in ways that we don't understand. These interactions could create additional drag forces or accelerations that would interfere with navigation and control. The dark matter effects might also become apparent at relativistic speeds. If dark matter interacts with ordinary matter through forces other than gravity, these interactions might only become significant at near-light speeds. The spacecraft could encounter drag forces or other effects from dark matter that would make travel more difficult or dangerous. The cosmic inflation analogy suggests that the early universe underwent a period of faster-than-light expansion. While this doesn't violate relativity because space itself was expanding rather than matter moving through space, it raises questions about whether similar effects could be harnessed for faster-than-light travel. However, the energy requirements for creating such effects would be astronomical. The wormhole possibilities that emerge from general relativity offer theoretical alternatives to near-light-speed travel, but they come with their own impossible requirements. Traversable wormholes would require exotic matter with negative energy density to keep them stable, and such matter might not exist in nature. Even if it does exist, the amounts required would be enormous. The Alcubierre drive concept proposes warping space-time to achieve effective faster-than-light travel without violating relativity locally. However, this would require exotic matter with negative energy density and would consume more energy than exists in the observable universe. The concept remains purely theoretical, with no prospect of practical implementation. The tachyon hypotheses propose particles that always travel faster than light, but such particles would have imaginary mass and would violate causality by allowing information to travel backward in time. No tachyons have ever been detected, and their existence would create paradoxes that would undermine the logical structure of physics. The tachyon paradoxes illustrate why faster-than-light travel creates fundamental problems with causality and the logical structure of the universe. If tachyons existed and could carry information, they would allow you to send messages to your own past, creating grandfather paradox scenarios where you could prevent your own birth or create logical contradictions that have no resolution. The universe seems to have built-in protections against such paradoxes. The chronology protection conjecture proposed by Stephen Hawking suggests that the laws of physics somehow prevent the formation of closed, time-like curves that would allow time travel. This protection might extend to faster-than-light travel, making it impossible not just for engineering reasons, but because it would violate the fundamental causal structure of space-time. The Novikov self-consistency principle offers an alternative approach, suggesting that any time travel that occurs must be self-consistent with the observed timeline. Under this principle, faster-than-light travel might be possible, but only in ways that don't create paradoxes. However, the constraints required to maintain consistency might make such travel effectively impossible. The many-worlds interpretation of quantum mechanics provides another perspective on faster-than-light travel paradoxes. In this view, traveling faster than light might split you into parallel universes, preventing paradoxes by ensuring that you can never return to your original timeline. However, this interpretation remains highly speculative and doesn't resolve the energy and engineering problems. The block universe concept from relativity suggests that all moments in time exist simultaneously, and our perception of flowing time is an illusion. In this view, faster-than-light travel wouldn't create paradoxes because the past, present, and future all exist equally. However, this doesn't change the physical impossibility of accelerating massive objects to light speed. The quantum entanglement phenomena that Einstein called spooky action at a distance demonstrate correlations that appear to operate faster than light, but these correlations cannot be used to transmit information. When you measure one entangled particle, you instantly know the state of its partner regardless of distance, but you cannot use this to send messages because the measurement results appear random until compared. The quantum tunneling effects allow particles to pass through energy barriers that should be classically forbidden, and some interpretations suggest this happens instantaneously. However, careful analysis shows that no information travels faster than light during tunneling, and the effect cannot be used for faster-than-light communication or travel. The EPR paradox proposed by Einstein, Podolsky, and Rosen was intended to show that quantum mechanics must be incomplete because it allows faster-than-light correlations. However, Bell's theorem and subsequent experiments have confirmed that these correlations are real and fundamental to to quantum mechanics, not evidence of hidden variables or incomplete theories. The aspect experiments and their successors have tested Bell's inequalities with increasing precision, confirming that quantum entanglement really does create instantaneous correlations across arbitrary distances. However, these experiments also confirm that the correlations cannot be used for faster-than-light communication, preserving the causal structure of spacetime. The delayed-choice quantum eraser experiments demonstrate even more bizarre quantum effects where future measurements seem to retroactively determine the behavior of past particles. However, careful analysis shows that no information travels backward in time, and the effects can be explained without violating causality or relativity. The quantum Zeno effect shows that frequent measurements can freeze the evolution of quantum systems, effectively stopping time for quantum particles. While this might seem to offer a route to manipulating time and space, the effect operates within the normal framework of quantum mechanics and doesn't violate relativity or enable faster-than-light travel. The quantum field theory complications at high energies reveal that our understanding of physics becomes incomplete at the extreme conditions required for near-light speed travel. The standard model of particle physics has been tested to incredible precision, but it breaks down at the Planck scale, where quantum gravity effects become important. The grand unified theories attempt to unify the electromagnetic, weak, and strong nuclear forces at high energies, but these theories remain largely untested and might not apply to the extreme conditions of relativistic travel. The energy scales required for near-light speed travel could reveal new physics that makes such travel even more impossible than current theories suggest. The theory of everything that physicists seek would unify quantum mechanics and general relativity, potentially revealing new insights about the fundamental limits of motion and causality. However, current candidates like string theory and loop quantum gravity suggest that these limits are even more restrictive than classical relativity implies. The anthropic principle considerations suggest that the laws of physics might be fine-tuned to allow the existence of observers like ourselves. The impossibility of faster-than-light travel might be necessary for the stability of causality and the logical structure of the universe. In universes where faster-than-light travel were possible, paradoxes might prevent the evolution of intelligent life. The multiverse theories propose that our universe is just one of many with different physical laws and constants. In some of these universes, faster-than-light travel might be possible, but we necessarily find ourselves in a universe where the laws of physics are compatible with our existence. The impossibility of faster-than-light travel in our universe might be an anthropic selection effect. The simulation hypothesis suggests that our reality might be a computer simulation running on some vast computational substrate. In this view, the speed of light might simply be the maximum rate at which information can be processed in the simulation. However, this hypothesis doesn't change the experienced reality of physical laws or make faster-than-light travel any more achievable. The holographic principle implications suggest that all the information in our three-dimensional universe might be encoded on a two-dimensional boundary. If this is true, the apparent three-dimensional motion through space might be an illusion, and faster-than-light travel might be meaningless because space itself might not be fundamental. The emergent spacetime theories propose that space and time arise from more fundamental information, theoretic processes. In these theories, the speed of light emerges as a property of how information propagates through the underlying computational substrate. Faster-than-light travel would require violating the fundamental information processing limits of reality itself. The digital physics approaches suggest that the universe operates like a cellular automaton with discrete time steps and spatial locations. In such a universe, the speed of light would be determined by the rate at which information can propagate through the computational grid. Exceeding this speed would be like trying to make a computer program run faster than its clock speed. The eit from bit hypothesis proposed by John Wheeler suggests that all physical phenomena arise from binary choices and information processing. In this view, matter and energy are emergent properties of information, and the speed of light represents the maximum rate at which binary information can propagate through the universe. The quantum information theory perspectives on space-time suggest that entanglement and quantum correlations might be the fundamental building blocks from which space and time emerge. The speed of light would then represent the maximum rate at which quantum information can be processed and transmitted, making faster-than-light travel equivalent to violating the fundamental computational limits of reality. The black hole information paradox reveals deep connections between gravity, quantum mechanics, and information theory that we don't fully understand. The resolution of this paradox might require new physics that further restricts the possibilities for faster-than-light travel, or reveals that our current understanding of space and time is fundamentally incomplete. The firewall paradox in black hole physics suggests that the smooth space-time predicted by general relativity might break down at event horizons, replaced by walls of high-energy radiation. If similar effects occur at the boundaries of light-speed travel, they could create additional barriers that make relativistic motion even more impossible than current theories suggest. The ER equals EPR conjecture proposes that quantum entanglement and wormholes are two descriptions of the same phenomenon. If this is true, the instantaneous correlations of quantum entanglement might be mediated by microscopic wormholes that connect distant regions of space-time. However, these wormholes would be far too small and unstable to allow macroscopic faster-than-light travel. The ER equals EPR conjecture opens up fascinating possibilities about the fundamental structure of space-time, but it also reveals why macroscopic faster-than-light travel remains impossible. These microscopic wormholes, if they exist, would be smaller than subatomic particles and would exist for incredibly brief moments before collapsing. The energy required to stabilize them for macroscopic travel would exceed the mass energy of entire galaxies. The ADS-CFT correspondence, one of the most important developments in theoretical physics, provides a mathematical framework for understanding how gravity in higher dimensions relates to quantum field theory on lower dimensional boundaries. This correspondence suggests that our three-dimensional reality might be a holographic projection from a higher dimensional space, but it doesn't provide any mechanism for faster-than-light travel within our experienced reality. The gauge-gravity duality implications reveal deep connections between quantum field theories and gravitational theories that we're only beginning to understand. These dualities might eventually lead to new insights about the fundamental nature of space and time, but current research suggests that they reinforce rather than eliminate the barriers to faster-than-light travel. The string theory landscape contains an estimated 10 to the 500th possible vacuum states, each with different physical laws and constants. In some of these universes, the speed of light might be different, or faster-than-light travel might be possible. However, we exist in a universe where the laws of physics make such travel impossible, and we have no way to access these alternative realities. The eternal inflation scenarios suggest that our observable universe is just one bubble in an infinite multiverse where all possible physical laws are realized somewhere. While this might mean that faster-than-light travel is possible in some regions of the multiverse, it doesn't help us overcome the barriers in our own cosmic neighborhood. The anthropic landscape reasoning suggests that we observe the physical constants we do because they're compatible with the existence of observers like ourselves. The impossibility of faster-than-light travel might be necessary for the stability of causality and the evolution of complex structures like stars, planets, and life. In universes where faster-than-light travel were common, the resulting paradoxes might prevent the formation of stable structures. The fine-tuning arguments reveal that many physical constants appear to be precisely calibrated to allow the existence of complexity and life. The speed of light is intimately connected to other fundamental constants through relationships like the fine structure constant. Changing the speed of light to allow faster-than-light travel might destabilize other aspects of physics that are necessary for our existence. The cosmic censorship hypothesis suggests that the universe has built-in mechanisms to prevent the formation of naked singularities that would violate the predictability of physics. Similar protection mechanisms might prevent faster-than-light travel to preserve the causal structure of space-time and prevent paradoxes that would undermine the logical consistency of the universe. The information-theoretic limits on computation and communication provide another perspective on why faster-than-light travel is impossible. The Bekenstein bound sets fundamental limits on how much information can be contained in a given region of space, and the Margolis-Levitin theorem limits how fast quantum systems can evolve. These limits suggest that faster-than-light travel would violate the fundamental computational capacity of the universe. The Landauer principle connects information processing to thermodynamics, showing that erasing information requires a minimum amount of energy. The energy costs of the information processing required for faster-than-light travel might exceed the energy available in the observable universe, providing yet another barrier to such travel beyond the relativistic mass-energy requirements. The quantum error correction mechanisms that maintain the stability of quantum information might also prevent faster-than-light travel. If space-time itself is a quantum error-correcting code, as some theories suggest, then faster-than-light travel might be equivalent to introducing uncorrectable errors that would destabilize the fabric of reality. The holographic error correction proposals suggest that the information in our universe is protected by quantum error correction mechanisms operating on the holographic boundary. These mechanisms might prevent faster-than-light travel by ensuring that information cannot propagate faster than the speed at which error correction can operate. The complexity theory perspectives on physics suggest that the universe operates like a vast quantum computer, with physical processes corresponding to computational operations. The speed of light might represent the maximum clock speed of this cosmic computer, making faster-than-light travel equivalent to trying to make the universe compute faster than its fundamental processing limits allow. The cellular automaton models of physics propose that space-time operates like a discrete computational grid, with the speed of light determined by how fast information can propagate from cell to cell. In these models, faster-than-light travel would require violating the fundamental update rules of the cosmic cellular automaton, which might be impossible by definition. The causal set approaches to quantum gravity suggest that space-time is fundamentally discrete, composed of individual events connected by causal relationships. In this framework, the speed of light emerges from the discrete structure of causality itself. Faster-than-light travel would require violating the causal ordering of events, which might be logically impossible. The loop quantum gravity predictions about the discrete structure of space-time at the Planck scale might impose additional barriers to faster-than-light travel. If space and time are quantized into indivisible units, then motion faster than light might be impossible because it would require traversing less than 1 unit of space in less than 1 unit of time. The spin foam models that describe space-time evolution in loop quantum gravity show how the discrete structure of space emerges from quantum processes. These models suggest that the speed of light is built into the fundamental quantum geometry of space-time, making faster-than-light travel equivalent to violating the basic rules of quantum geometry. The asymptotic safety scenarios for quantum gravity propose that the theory becomes well-defined at all energy scales through the existence of a non-trivial fixed point. These scenarios might impose additional constraints on high-energy physics that make faster-than-light travel even more impossible than classical general relativity suggests. The emergent gravity theories propose that gravitational forces arise from more fundamental quantum entanglement and information-theoretic processes. In these theories, the speed of light emerges from the fundamental properties of quantum information, making faster-than-light travel equivalent to violating the basic principles of quantum mechanics. The entropic force proposals suggest that gravity itself is an entropic force arising from the tendency of systems to maximize entropy. If this is true, then the speed of light might be related to the maximum rate at which entropy can increase, providing a thermodynamic barrier to faster-than-light travel. The thermodynamic arrow of time that distinguishes past from future is intimately connected to the speed of light and causality. Faster-than-light travel could potentially violate this arrow of time, creating paradoxes where entropy decreases and effects precede their causes. The universe's commitment to increasing entropy might provide another fundamental barrier to such travel. The second law of thermodynamics requires that entropy always increases in isolated systems. Faster-than-light travel might violate this law by allowing information to travel backward in time, potentially enabling the creation of perpetual motion machines or other violations of thermodynamic principles. The Maxwell's demon thought experiment illustrates the deep connections between information, entropy, and thermodynamics. If faster-than-light travel were possible, it might enable the creation of Maxwell's demon-like devices that could violate the second law of thermodynamics by using faster-than-light information to sort molecules and decrease entropy. The Landauer erasure principle shows that erasing information requires a minimum amount of energy and generates heat. The information processing required for faster-than-light travel might require erasing enormous amounts of information, generating so much waste heat that it would be impossible to dissipate, creating another thermodynamic barrier to such travel. The quantum thermodynamics extensions of classical thermodynamics to quantum systems reveal additional constraints on information processing and energy conversion. These constraints might impose fundamental limits on the efficiency of any propulsion system, making the energy requirements for faster-than-light travel even more prohibitive than classical calculations suggest. The fluctuation theorems that describe how thermodynamic quantities behave in small systems and short timescales might impose additional constraints on faster-than-light travel. These theorems show that violations of the second law of thermodynamics become increasingly unlikely as system size and timescales increase, making macroscopic faster-than-light travel thermodynamically forbidden. The fluctuation theorems reveal that while small-scale violations of thermodynamic laws are possible for brief moments, the probability of large-scale violations decreases exponentially with the size and duration of the violation. A spacecraft achieving faster-than-light travel would represent such a massive thermodynamic violation that its probability would be essentially zero, providing a statistical argument against the possibility of such travel. The Jarzynski equality and Crookes fluctuation theorem show how thermodynamic work and heat are related in non-equilibrium processes. The extreme non-equilibrium conditions required for faster-than-light travel might violate these fundamental relationships, creating thermodynamic impossibilities that go beyond simple energy conservation arguments. The quantum heat engines and refrigerators that operate on quantum mechanical principles face fundamental efficiency limits imposed by the laws of thermodynamics. Any propulsion system capable of faster-than-light travel would need to operate with efficiencies that violate these quantum thermodynamic limits, making such systems physically impossible. The information engines that convert information into work face fundamental limits imposed by the connection between information and thermodynamics. The information processing required for faster-than-light navigation and control might require more energy than could be extracted from any conceivable fuel source, creating an information-theoretic barrier to such travel. The quantum resource theories that describe how quantum properties like entanglement and coherence can be used as resources for information processing reveal fundamental limits on what can be achieved with quantum systems. These limits might constrain the quantum technologies that would be required for faster-than-light travel, making such travel impossible even with perfect quantum computers. The quantum supremacy demonstrations that show quantum computers can solve certain problems exponentially faster than classical computers still operate within the fundamental limits imposed by the speed of light and causality. Even quantum computers cannot violate these limits, and they cannot enable faster-than-light communication or travel. The quantum teleportation protocols that allow the transfer of quantum states between distant locations still require classical communication at light speed to complete the process. While quantum information can be transferred instantaneously, the classical information needed to decode it must travel at light speed, preserving causality and preventing faster-than-light communication. The quantum cryptography systems that use quantum mechanics to ensure secure communication rely on the impossibility of faster-than-light communication to guarantee their security. If faster-than-light travel were possible, it could potentially break these cryptographic systems by allowing eavesdroppers to intercept and retransmit quantum information faster than light. The quantum sensing technologies that use quantum effects to make ultra-precise measurements are limited by the fundamental quantum limits imposed by the uncertainty principle and the speed of light. These limits constrain the precision with which position, velocity, and other quantities can be measured, making the navigation required for faster-than-light travel fundamentally impossible. The quantum metrology protocols that achieve the ultimate precision allowed by quantum mechanics still cannot overcome the fundamental barriers imposed by relativity and causality. Even with perfect quantum sensors, the measurement and control systems required for faster-than-light travel would face insurmountable physical limitations. The decoherence processes that cause quantum systems to lose their quantum properties and behave classically would be accelerated at the extreme conditions required for faster-than-light travel. The quantum coherence needed for exotic propulsion systems would be destroyed by interactions with the environment, making such systems impossible to maintain. The quantum Darwinism mechanisms that explain how classical reality emerges from quantum mechanics through environmental monitoring would be disrupted at faster-than-light speeds. The information processing required for this emergence might be limited by the speed of light, making faster-than-light travel incompatible with the existence of classical reality. The measurement problem in quantum mechanics, which asks how and when quantum superpositions collapse into definite states, becomes even more complex at relativistic speeds. The faster-than-light travel might require resolving this problem in ways that are currently beyond our understanding, adding another layer of impossibility to such travel. The Quantum Foundations research that seeks to understand the fundamental nature of quantum mechanics reveals deep connections between quantum theory and the structure of space-time. These connections suggest that faster-than-light travel might require violating the basic principles of quantum mechanics, making it impossible even in principle. The interpretational issues in quantum mechanics, such as the many-worlds interpretation and the Copenhagen interpretation, have different implications for faster-than-light travel. However, none of these interpretations provide a clear path to achieving such travel, and most suggest additional barriers that make it even more impossible. The quantum field theory in curved space-time that describes how quantum mechanics and general relativity interact reveals additional complications for faster-than-light travel. The extreme space-time curvature required for such travel might create quantum effects that destabilize the spacecraft or make travel impossible. The Hawking radiation that black holes emit due to quantum effects near their event horizons might also occur around spacecraft traveling at near-light speeds. The extreme conditions could create virtual particle pairs that separate, leading to radiation emission that would drain energy from the spacecraft and create additional hazards. The Unruh effect that causes accelerated observers to detect thermal radiation in empty vacuum would become extreme for spacecraft undergoing the accelerations required for faster-than-light travel. The perceived temperature of this radiation could become so high that it would destroy any known materials, making the spacecraft uninhabitable. The Casimir effect that creates attractive forces between conducting surfaces due to quantum vacuum fluctuations could be dramatically altered at faster-than-light speeds. These modifications might create additional forces that interfere with spacecraft operation or require additional energy to overcome. The vacuum polarization effects that occur in strong electromagnetic fields could become significant around faster-than-light spacecraft. The intense fields generated by such motion might create electron-positron pairs from the vacuum, leading to energy loss and radiation hazards that would make travel impossible. The quantum vacuum fluctuations that constantly create and destroy virtual particles throughout space might interact with faster-than-light spacecraft in unpredictable ways. These interactions could create drag forces, radiation, or other effects that would prevent such travel or make it extremely dangerous. The zero-point energy of the quantum vacuum represents the lowest possible energy state of quantum fields, but it still contains enormous amounts of energy. Some speculative proposals suggest harnessing this energy for propulsion, but the engineering challenges would be insurmountable, and the energy extraction might violate fundamental principles of quantum mechanics. The cosmological constant problem, which asks why the observed vacuum energy density is so much smaller than theoretical predictions, reveals deep mysteries about the nature of empty space. These mysteries might be related to fundamental limits on energy extraction from the vacuum that would make exotic propulsion systems impossible. The dark energy that drives the accelerating expansion of the universe represents a form of energy that fills all of space but cannot be harnessed for practical purposes. The properties of dark energy might impose additional constraints on faster-than-light travel that we don't currently understand. The cosmic inflation that occurred in the early universe involved faster-than-light expansion of space itself, but this didn't violate relativity because space was expanding rather than matter moving through space. Attempts to harness similar effects for propulsion would require energy densities comparable to those in the early universe, making them completely impractical. The multiverse theories that emerge from cosmic inflation suggest that our universe is just one bubble in an infinite collection of universes with different physical laws. While faster-than-light travel might be possible in some of these universes, we have no way to access them, and we're stuck with the laws of physics in our own cosmic bubble. The anthropic reasoning that explains why we observe the physical constants we do suggests that faster-than-light travel might be impossible in any universe that can support the evolution of intelligent observers. The causal paradoxes created by such travel might prevent the formation of stable structures necessary for life and intelligence. The fine-tuning of physical constants that allows the existence of atoms, stars, planets, and life might be incompatible with faster-than-light travel. Changing the fundamental constants to allow such travel might destabilize other aspects of physics that are necessary for the existence of complex structures and intelligent observers. The fine-tuning arguments become even more compelling when we consider how interconnected the fundamental constants of nature really are. The speed of light isn't an isolated parameter. It's woven into the fabric of reality through relationships with the electric permittivity and magnetic permeability of free space, the fine structure constant, and dozens of other fundamental quantities. Changing any of these to allow faster-than-light travel would likely destabilize the delicate balance that makes atoms, chemistry, and life possible. The hierarchy problem in particle physics asks why gravity is so much weaker than the other fundamental forces. Some theories propose that gravity operates in extra dimensions that we can't directly perceive, which could potentially provide shortcuts for faster-than-light travel. However, these extra dimensions would need to be either incredibly small or completely inaccessible to ordinary matter, making them useless for practical transportation. The extra dimensions predicted by string theory and other unified theories might seem to offer possibilities for faster-than-light travel through higher dimensional shortcuts. However, these dimensions are either compactified to sizes smaller than subatomic particles or separated from our three-dimensional space in ways that make them inaccessible to macroscopic objects like spacecraft. The Kaluza-Klein theories that attempt to unify gravity with other forces through extra dimensions face enormous technical challenges that make them unsuitable for practical applications. The energy scales required to access these dimensions would exceed anything achievable with conceivable technology, and the stability problems would make any such access extremely dangerous. The brain-world scenarios that propose our universe is a three-dimensional membrane floating in higher dimensional space might allow for shortcuts through the bulk dimensions. However, leaving our brain would likely be fatal to any form of matter that evolved within our three-dimensional space, making such shortcuts useless for travel, even if they were accessible. The warped product spacetimes that emerge from some theories of extra dimensions could potentially create regions where the effective speed of light is different. However, these regions would likely be unstable and would require exotic matter or energy conditions that don't exist in nature, making them impossible to create or maintain artificially. The compactification mechanisms that hide extra dimensions from our direct observation involve energy scales that are far beyond anything we can manipulate. The forces required to decompactify these dimensions would be comparable to those present during the Big Bang, making any practical application completely impossible with conceivable technology. The moduli stabilization problems in string theory reveal that extra dimensions are inherently unstable and require fine-tuning to maintain their compactified state. Any attempt to manipulate these dimensions for faster-than-light travel would likely destabilize them, potentially destroying the local region of spacetime and making travel impossible. The landscape problem in string theory, with its vast number of possible vacuum states, suggests that most configurations of extra dimensions would be incompatible with the existence of stable matter and energy. The configurations that do allow for stable physics might be precisely those that prohibit faster-than-light travel. The swampland conjectures in string theory propose that most seemingly consistent theories of quantum gravity are actually inconsistent when examined more carefully. These conjectures might rule out the exotic space-time geometries and matter configurations that would be required for faster-than-light travel, making such travel impossible even in principle. The weak gravity conjecture suggests that gravity must be the weakest force in any consistent theory of quantum gravity. This constraint might prevent the creation of the exotic matter and energy configurations that would be required for faster-than-light propulsion systems, adding another fundamental barrier to such travel. The distance conjecture proposes that as you move far in the space of possible theories, some particles become massless and the theory breaks down. This might prevent the creation of stable, faster-than-light propulsion systems by ensuring that any attempt to build such systems would destabilize the underlying physics. The de Sitter swampland conjecture suggests that universes with positive cosmological constants like ours might be fundamentally unstable. If this is true, then our universe might be inherently unsuitable for the exotic physics required for faster-than-light travel, making such travel impossible in any stable cosmological setting. The Trans-Planckian problem in cosmology reveals that our understanding of physics breaks down at energy scales approaching the Planck scale. The energy densities required for faster-than-light travel might approach these scales, taking us into regimes where our current theories are no longer valid and new, unknown physics takes over. The black hole information paradox reveals deep inconsistencies between quantum mechanics and general relativity that we don't know how to resolve. The extreme conditions required for faster-than-light travel might exacerbate these inconsistencies, creating paradoxes that make such travel logically impossible. The firewall paradox suggests that the smooth space-time predicted by general relativity might break down at black hole event horizons, replaced by walls of high-energy radiation. Similar effects might occur at the boundaries of faster-than-light travel, creating barriers that would destroy any spacecraft attempting to cross them. The holographic principle implications for faster-than-light travel suggest that all the information in a volume of space can be encoded on its boundary. If this is true, then faster-than-light travel might be impossible because it would require processing more information than can be contained in the relevant spatial region. The holographic entanglement entropy that connects quantum entanglement to space-time geometry might impose fundamental limits on faster-than-light travel. The entanglement structure required to maintain space-time coherence during such travel might be impossible to preserve, leading to the breakdown of space-time itself. The ADS-CFT correspondence that relates gravity theories to quantum field theories on their boundaries suggests that faster-than-light travel in the bulk space-time might be equivalent to violating causality in the boundary theory. This equivalence might make faster-than-light travel impossible by connecting it to logical contradictions in quantum field theory. The tensor network models of space-time that emerge from holographic theories suggest that space itself is built from quantum entanglement. Faster-than-light travel might require breaking these entanglement connections, potentially causing space-time to disintegrate and making travel impossible. The quantum error correction mechanisms that might protect space-time from quantum decoherence could also prevent faster-than-light travel. If space-time is a quantum error-correcting code, then faster-than-light travel might introduce uncorrectable errors that would destabilize the fabric of reality. The complexity theory perspectives on space-time suggest that the universe operates like a quantum computer, with physical processes corresponding to computational operations. The computational complexity of faster-than-light travel might exceed the processing capacity of the universe itself, making such travel impossible, even in principle. The quantum supremacy results that demonstrate the power of quantum computers still operate within the fundamental limits imposed by causality and the speed of light. Even with perfect quantum computers, the information processing required for faster-than-light travel might be impossible due to these fundamental constraints. The quantum machine learning algorithms that can solve certain problems exponentially faster than classical algorithms still cannot violate the speed of light or enable faster-than-light communication. The quantum advantages come from exploiting quantum superposition and entanglement, not from violating relativistic causality. The quantum simulation capabilities that allow quantum computers to simulate other quantum systems efficiently still face fundamental limits imposed by the speed of light and causality. Even perfect quantum simulators cannot simulate faster-than-light travel because such travel violates the basic principles on which quantum mechanics is built. The quantum sensing technologies that achieve unprecedented precision in measuring physical quantities are still limited by the fundamental quantum limits imposed by the uncertainty principle and the finite speed of light. These limits constrain the precision with which the position and velocity of spacecraft can be measured and controlled. The quantum communication protocols that enable secure communication using quantum mechanics still require classical communication channels that operate at the speed of light. The quantum advantages come from the security provided by quantum mechanics, not from faster-than-light communication capabilities. The quantum cryptography systems that use quantum mechanics to ensure information security rely on the impossibility of faster-than-light communication to guarantee their effectiveness. If faster-than-light travel were possible, it might enable new forms of attack that could compromise these security systems. The quantum internet proposals that would connect quantum computers around the world still face the fundamental limitation that quantum information cannot be transmitted faster than light. The quantum internet would enable new forms of distributed quantum computing, but it would not enable faster-than-light communication or travel. The quantum teleportation protocols that can transfer quantum states between distant locations still require classical communication at light speed to complete the transfer. The quantum state can be transferred instantaneously, but the classical information needed to reconstruct it must travel at light speed, preserving causality. The quantum key distribution systems that enable provably secure communication use quantum mechanics to detect eavesdropping attempts. These systems rely on the fundamental principles of quantum mechanics and the impossibility of faster-than-light communication to provide their security guarantees. The quantum key distribution systems reveal another fundamental aspect of why faster-than-light travel remains impossible. The security of these systems depends on the inviolability of causality and the speed of light limit. If faster-than-light communication were possible, an eavesdropper could potentially intercept quantum information, process it using faster-than-light systems, and retransmit it before the original transmission was complete, breaking the fundamental security guarantees that quantum mechanics provides. The no-cloning theorem in quantum mechanics states that arbitrary quantum states cannot be perfectly copied. This theorem is intimately connected to the structure of space-time and causality. If faster-than-light travel were possible, it might enable violations of the no-cloning theorem by allowing quantum information to be transmitted to the past and copied before it was originally created, creating logical paradoxes. The quantum Zeno effect demonstrates that frequent measurements can freeze the evolution of quantum systems, but this effect operates within the normal framework of quantum mechanics and relativity. While it might seem to offer a way to manipulate time and space, the effect cannot be used to achieve faster-than-light travel because it doesn't violate the fundamental causal structure of space-time. The quantum tunneling phenomena that allow particles to pass through energy barriers instantaneously might seem to offer hope for faster-than-light travel. However, careful analysis shows that while the tunneling process itself appears instantaneous, no information or energy travels faster than light during the process. The apparent faster-than-light motion is an artifact of how we define the tunneling time. The Hartmann effect in quantum tunneling shows that the tunneling time becomes independent of barrier width for sufficiently thick barriers, leading to apparent superluminal velocities. However, this effect cannot be used for faster-than-light communication because the transmitted signal is severely attenuated and distorted, making it impossible to send meaningful information. The group velocity and phase velocity distinctions in wave propagation reveal that different aspects of waves can travel at different speeds. While phase velocity can exceed the speed of light in certain materials, the group velocity that carries information and energy always remains below the speed of light, preserving causality and preventing faster-than-light communication. The negative group velocity phenomena observed in certain materials create the illusion that light pulses exit a medium before they finish entering it. However, careful analysis shows that no information travels faster than light. The effect is caused by the reshaping of the pulse as it interacts with the medium, not by genuine faster-than-light propagation. The superluminal phase velocities that can be achieved in metamaterials and other exotic media might seem to offer possibilities for faster-than-light travel. However, these effects only apply to the phase of electromagnetic waves, not to the energy or information content. The fundamental speed limit for information and energy transfer remains unchanged. The evanescent waves that exist near the surfaces of certain materials can have phase velocities that exceed the speed of light. However, these waves decay exponentially with distance and cannot propagate through free space, making them useless for faster-than-light communication or travel over macroscopic distances. The Cherenkov radiation that occurs when charged particles move through a medium faster than light travels in that medium might seem to demonstrate faster-than-light motion. However, the particles are still moving slower than the speed of light in vacuum, and the effect occurs because light is slowed down by the medium, not because the particles exceed the fundamental speed limit. The tachyonic fields that appear in some quantum field theories as mathematical artifacts during symmetry breaking do not correspond to physical particles that travel faster than light. These fields are unstable and decay into normal, slower-than-light particles, and they cannot be used to achieve faster-than-light travel or communication. The space-like separated events in relativity that cannot be connected by light signals reveal the fundamental structure of causality in spacetime. Faster-than-light travel would connect space-like separated events, potentially allowing effects to precede their causes and creating paradoxes that would undermine the logical consistency of physics. The light cone structure of spacetime defines the regions that can be causally connected to any given event. Faster-than-light travel would violate this structure by allowing signals to propagate outside the light cone, potentially enabling communication with the past and creating grandfather paradox scenarios that have no logical resolution. The relativity of simultaneity shows that events that are simultaneous in one reference frame are not simultaneous in another frame moving at high velocity. Faster-than-light travel would exacerbate this effect, potentially allowing travelers to arrive at their destination before they departed, creating temporal paradoxes that violate causality. The twin paradox in special relativity demonstrates how time dilation affects travelers moving at high speeds relative to stationary observers. At faster-than-light speeds, this paradox would become even more severe, potentially allowing travelers to return to their starting point before they left, creating impossible causal loops. The ladder paradox and other relativity paradoxes reveal how length contraction and time dilation create apparent contradictions that are resolved by careful analysis of simultaneity and reference frames. Faster-than-light travel would create similar but more severe paradoxes that might not have any consistent resolution. The causal structure of spacetime in general relativity becomes even more complex in the presence of strong gravitational fields and curved spacetime. Faster-than-light travel in such environments could create closed time-like curves that allow travel to the past, creating paradoxes that would violate the fundamental principles of causality. The Gödel universe, a solution to Einstein's field equations that allows closed time-like curves throughout spacetime, demonstrates that general relativity permits time travel under certain conditions. However, these conditions require exotic matter distributions that don't exist in our universe, and the resulting spacetime would be unstable and unsuitable for life. The Alcubierre warp drive concept attempts to achieve faster-than-light travel by warping spacetime rather than moving through it at superluminal speeds. However, this concept requires exotic matter with negative energy density that might not exist in nature, and the energy requirements would exceed the mass energy of the observable universe. The Krasnikov tube proposal suggests creating a spacetime tunnel that would allow faster-than-light travel between distant locations. However, like the Alcubierre drive, this concept requires exotic matter and enormous energy expenditures that make it completely impractical with any conceivable technology. The traversable wormhole solutions to Einstein's equations could theoretically allow faster-than-light travel by providing shortcuts through higher dimensional space. However, these solutions require exotic matter to keep the wormholes stable, and quantum effects would likely cause them to collapse before anything could pass through them. The Morris-Thorne wormholes that could theoretically be traversed by macroscopic objects require exotic matter with negative energy density distributed throughout the wormhole throat. The amount of exotic matter required would be enormous, and we have no evidence that such matter exists in nature or can be created artificially. The quantum inequalities that constrain the behavior of quantum fields in curved spacetime might prevent the creation of the exotic matter required for wormholes and warp drives. These inequalities show that negative energy densities can only exist for brief periods and in limited quantities, making stable, faster-than-light propulsion systems impossible. The average null energy condition and other energy conditions in general relativity constrain the types of matter and energy that can exist in curved spacetime. These conditions might prohibit the exotic matter configurations required for faster-than-light travel, making such travel impossible even in principle. The quantum field theory in curved spacetime reveals additional constraints on faster-than-light travel that emerge from the interaction between quantum mechanics and general relativity. The Hawking radiation from black holes and the Unruh effect for accelerated observers demonstrate that quantum effects become important in extreme gravitational environments. The trans-Planckian problem in black hole physics shows that our understanding of quantum field theory breaks down at extremely high energies and small-length scales. The conditions required for faster-than-light travel might involve trans-Planckian physics that we don't understand, making it impossible to predict whether such travel is feasible. The black hole complementarity principle attempts to resolve the information paradox by suggesting that information falling into a black hole is simultaneously destroyed and preserved depending on the observer's reference frame. This principle might impose similar constraints on faster-than-light travel by preventing information from being transmitted in ways that would violate causality. The holographic principle's implications for black hole physics suggest that all the information about the black hole's interior is encoded on its surface. If similar principles apply to faster-than-light travel, they might prevent such travel by ensuring that all information about the journey is constrained to propagate at the speed of light. The firewall paradox in black hole physics suggests that the event horizon might be replaced by a wall of high-energy radiation that would destroy anything attempting to cross it. Similar firewalls might exist at the boundaries of faster-than-light travel, creating barriers that would make such travel impossible or fatal. The ER equals EPR conjecture that connects wormholes to quantum entanglement suggests that the instantaneous correlations of entangled particles might be mediated by microscopic wormholes. However, these wormholes would be far too small and unstable to allow macroscopic faster-than-light travel, and they cannot be used for communication. The ER equals EPR conjecture reveals a profound truth about the nature of spacetime and quantum mechanics. Even if microscopic wormholes connect entangled particles, they operate at scales so small and for durations so brief that they're completely useless for macroscopic faster-than-light travel. These quantum scale connections exist at the Planck length, roughly 10 to the negative 35 meters, making them smaller than the ratio between an atom and the observable universe. The quantum foam structure of spacetime at the Planck scale suggests that space and time themselves become uncertain and fluctuating at the smallest scales. These fluctuations might create temporary microscopic wormholes and other exotic spacetime geometries, but they would be far too small and unstable to exploit for faster-than-light travel, existing for only about 10 to the negative 43 seconds before collapsing. The holographic noise that emerges from the discrete structure of spacetime at the Planck scale might impose fundamental limits on the precision with which position and time can be measured. This noise could make the navigation and control systems required for faster-than-light travel fundamentally impossible, adding another layer of impossibility to such endeavors. The causal dynamical triangulation approaches to quantum gravity suggest that space-time emerges from discrete building blocks at the Planck scale. In these models, the speed of light emerges from the discrete structure of space-time itself, making faster-than-light travel equivalent to violating the fundamental rules that govern the existence of space and time. The asymptotic safety program in quantum gravity proposes that the theory becomes well-defined at all energy scales through the existence of a non-trivial fixed point. If this program is successful, it might impose additional constraints on high-energy physics that make faster-than-light travel even more impossible than current theories suggest. The emergent gravity scenarios that propose gravitational forces arise from more fundamental quantum information processes suggest that space-time itself is an emergent phenomenon. In these theories, the speed of light emerges from the fundamental properties of quantum information, making faster-than-light travel equivalent to violating the basic computational limits of reality. The entropic force proposals that suggest gravity is a thermodynamic force arising from the tendency of systems to maximize entropy connect the speed of light to fundamental thermodynamic principles. Faster-than-light travel might violate these principles by allowing entropy to decrease or by enabling the creation of perpetual motion machines. The holographic entanglement entropy that connects the amount of quantum entanglement in a region to the area of its boundary might impose fundamental limits on faster-than-light travel. The entanglement structure required to maintain space-time coherence during such travel might exceed the maximum entanglement that can be contained in the relevant spatial region. The quantum error correction mechanisms that might protect space-time from decoherence could also prevent faster-than-light travel by ensuring that information cannot propagate faster than the speed at which error correction can operate. If space-time is a quantum error-correcting code, then faster-than-light travel might introduce uncorrectable errors that would destabilize reality itself. The complexity theory, perspectives on space-time that suggest the universe operates like a quantum computer, reveal fundamental computational limits that might constrain faster-than-light travel. The computational complexity of simulating faster-than-light motion might exceed the processing capacity of the universe itself, making such motion impossible even in principle. The it from bit hypothesis that proposes all physical phenomena arise from binary information processing suggests that the speed of light represents the maximum rate at which binary information can be processed in the universe. Faster-than-light travel would require processing information faster than this fundamental limit, which might be logically impossible. The digital physics approaches that model the universe as a cellular automaton or discrete computational system suggest that the speed of light is determined by the update rate of the cosmic computer. Exceeding this speed would be like trying to make a computer program run faster than its clock speed, which is impossible by definition. The quantum cellular automaton models of space-time propose that the universe evolves through discrete time steps according to local update rules. In these models, the speed of light emerges from the rate at which information can propagate from cell to cell, making faster-than-light travel equivalent to violating the fundamental update rules of reality. The tensor network representations of quantum many-body systems that might describe space-time suggest that the speed of light is related to the maximum rate at which quantum information can propagate through the network. Faster-than-light travel would require exceeding this information propagation limit, which might be impossible due to the structure of quantum mechanics. The machine learning approaches to understanding quantum many-body systems reveal fundamental limits on how quickly information can be processed and transmitted in quantum systems. These limits might constrain the quantum technologies that would be required for faster-than-light travel, making such travel impossible even with perfect quantum computers. The quantum supremacy demonstrations that show quantum computers can solve certain problems exponentially faster than classical computers still operate within the fundamental limits imposed by causality and the speed of light. The quantum advantages come from exploiting quantum parallelism and interference, not from violating relativistic constraints. The quantum advantage in communication complexity that allows quantum systems to solve certain communication problems more efficiently than classical systems still cannot enable faster-than-light communication. The quantum advantages come from reducing the amount of information that needs to be transmitted, not from transmitting it faster than light. The quantum sensing and metrology applications that achieve unprecedented precision in measuring physical quantities are still limited by the fundamental quantum limits imposed by the uncertainty principle and the finite speed of light. These limits constrain the precision with which spacecraft position and velocity can be measured and controlled. The quantum simulation capabilities that allow quantum computers to efficiently simulate other quantum systems face fundamental limits when attempting to simulate faster-than-light phenomena. These limits arise because faster-than-light motion violates the basic principles on which quantum mechanics is built. The quantum machine learning algorithms that can recognize patterns and solve optimization problems exponentially faster than classical algorithms still cannot overcome the fundamental barriers to faster-than-light travel. The quantum advantages come from exploiting quantum superposition and entanglement within the constraints of causality. The quantum artificial intelligence systems that might eventually surpass human intelligence in all domains would still be constrained by the fundamental laws of physics. Even superintelligent quantum AI systems could not enable faster-than-light travel because such travel violates the basic structure of space-time and causality. The technological singularity scenarios that propose exponential growth in technological capabilities would still be constrained by fundamental physical limits. No amount of technological advancement can overcome the basic impossibility of faster-than-light travel because this impossibility is built into the structure of reality itself. The Kardashev scale that classifies civilizations by their energy consumption suggests that advanced civilizations might harness the energy output of entire stars or galaxies. However, even Type 3 civilizations that control galactic-scale energy sources would still be unable to achieve faster-than-light travel because the barriers are fundamental rather than technological. The Fermi paradox that asks why we haven't encountered evidence of extraterrestrial civilizations might be partially explained by the impossibility of faster-than-light travel. If interstellar travel is limited to slower-than-light speeds, then even advanced civilizations would be constrained to their local stellar neighborhoods, making contact between civilizations extremely unlikely. The Drake equation that attempts to estimate the number of communicating civilizations in our galaxy assumes that such civilizations can communicate across interstellar distances. However, the impossibility of faster-than-light communication means that any such communication would involve delays of years to centuries, making meaningful dialogue between civilizations extremely difficult. The Great Filter hypothesis that suggests there are evolutionary bottlenecks that prevent most life from reaching technological sophistication might include the realization that faster-than-light travel is impossible. Civilizations that discover this fundamental limitation might lose motivation for space exploration and technological advancement. The zoo hypothesis that proposes advanced civilizations are deliberately avoiding contact with less developed species like humanity assumes that such civilizations have the capability for interstellar travel and communication. The impossibility of faster-than-light travel makes such widespread galactic civilizations much less likely. The simulation hypothesis that suggests our reality might be a computer simulation running on some vast computational substrate would still be constrained by the fundamental limits of information processing. Even simulated realities must respect basic logical consistency, and faster-than-light travel creates logical paradoxes that would destabilize any simulation. The anthropic principle considerations suggest that we observe the physical laws we do because they're compatible with the existence of observers like ourselves. The impossibility of faster-than-light travel might be necessary for the stability of causality and the evolution of complex structures like stars, planets, and life. The fine-tuning arguments that reveal how precisely calibrated the fundamental constants must be to allow the existence of complexity and life extend to the speed of light and its relationship to other physical constants. Changing these constants to allow faster-than-light travel would likely destabilize other aspects of physics that are necessary for our existence. The multiverse theories that propose our universe is just one of many, with different physical laws suggest that faster-than-light travel might be possible in some universes. However, we exist in a universe where such travel is impossible, and we have no way to access these alternative realities, even if they exist. The eternal inflation scenarios that suggest our observable universe is just one bubble in an infinite multiverse where all possible physical laws are realized somewhere don't help us overcome the barriers to faster-than-light travel in our own cosmic neighborhood. We're constrained by the laws of physics in our particular bubble universe. The landscape of string theory, with its vast number of possible vacuum states, might include configurations where faster-than-light travel is possible. However, most of these configurations would be unstable or incompatible with the existence of stable matter and energy, making them unsuitable for life and civilization. Enjoyed this video? I am sure you will love this other one at the left side of the screen. Does gravity really travel faster than light? In this video, we unravel one of the most profound questions in physics. How fast does gravity move, and what does that reveal about the fabric of space-time? See you there.